Hello everybody, let's talk about balancing redox reactions. We are well acquainted with the idea of balancing chemical equations. We did this in Chem 1, mostly. With redox reactions, it's going to be a little bit more complex. We're going to have to deal with not just balancing the number of atoms, which is what we dealt with in Chem 1. We are also going to have to deal with balancing the charge. Balancing the number of electrons on one side of a reaction versus another. When we're talking about really simple redox reactions, sometimes this does work itself out. Sometimes we don't have to take any special considerations. But for the types of redox reactions we're going to be looking at in this chapter, the type of redox reactions where you would use to make a voltaic cell, for example, we are going to have to take a more complex approach to balancing these things. Because while it might be one thing to balance the number of atoms, balancing the charge is a completely different thing. So we are going to have a process that we use to balance redox reactions. And the nice thing is, in Gen Chem 1, when we were balancing stuff, at least if you took my class, we kind of just treated it like a puzzle. We didn't really have a set do this thing, do this thing, do this thing, now you're done. Like there wasn't a step-by-step process. For redox reactions, we have a step-by-step process. We have a process that will work for every redox reaction you ever come across, and as long as you follow the steps, you will get the right answer. It's just a matter of following the steps correctly. And this process is what we call the half-reaction method. What the half-reaction method does is it involves treating the reaction just on paper. Obviously, this is an actual real life here, but on paper, we're going to treat the reaction as if it is two separate processes. We will balance those two separate processes and then combine them together to get the balanced equation for the overall reaction. So let's talk about this, the steps we're going to use to do this. So the first thing we're going to do is we're going to assign oxidation numbers to figure out what's oxidized and what's reduced. Sometimes we actually won't do this. Sometimes we'll be able to skip over this because it's fairly obvious what the two half reactions are. But if it's not completely obvious what the half reactions are, we might have to assign oxidation numbers. Number two, we're going to write the two half reactions. So we're going to split the reaction up into the two parts. The thing that gets oxidized, that will have its own half reaction. The thing that is reduced will have its own half reaction. We're then going to look at each of these two half reactions, and we're going to balance them using these steps, and these are in order as well. So the first thing we're going to do is we're going to balance everything other than hydrogen and oxygen. And this is almost always extraordinarily easy. Sometimes it doesn't even have to be done. Sometimes it's already balanced. If it's not balanced already, it's usually just, you have one chlorine on the left, you have two on the right, and so you just need to put another thing with a chlorine on the left. It's very straightforward. Second part here, once you have everything other than hydrogen and oxygen balanced, you're going to balance the oxygen. This is where it gets different from what we've done before. Other than splitting it into two, this is where it gets very different. We are going to balance oxygen by adding water. So if you have two oxygens on the left and only one oxygen on the right side of an equation, you're going to add a water to the right side of the equation to get that extra oxygen that you need. Once you've done that, if your hydrogen is not balanced, you're going to balance the hydrogen by adding H+. Again, very different from what we did balancing stuff in Gen Chem 1. In Gen Chem 1, to balance, we said the only thing we can do is change the coefficient. Not anymore. Now we are actually adding stuff in. So we're going to add in H+ to balance out the hydrogen. And then the last thing here for these half reactions is we are going to balance the charge by adding electrons. So we're going to add up the actual charge of everything that's involved in the reaction, and we are going to add electrons to get those charges on the left and right side of the equation to be equal to each other. And you should always have to add at least one electron only to one side of the equation. You will never add electrons to both, because then at that point you're just canceling yourself out. So you'll only add it to one side or the other, and you will always have to add at least one. If you get to this point, if you get to part D here, and it's already balanced in terms of charge, you did something wrong. You will always have to add at least one electron to one side or the other. Sometimes 2 electrons, sometimes 3, sometimes 5. It just depends on what it is you're looking at. Usually not 5. Usually just 1, 2, or maybe 3. But it is possible. Okay. So once you have the two half reactions individually balanced, you're going to multiply the two half reactions by integers so that the electrons gained and lost are the same. So if, for example, one of your half reactions, there are 2 electrons being transferred, and in the other one, only 1 electron is being transferred, what you're going to do is you're going to take this half reaction that only has 1 being transferred, and just everything inside of there gets multiplied by 2. You need the number of electrons being transferred in one half reaction versus the other to be the same. Number 5, add the two half reactions together, subtracting things that appear on both sides. And really it should say canceling. Well, if I could spell canceling. Canceling. So if you have, for example, 2 waters on the left side of the reaction and 3 waters on the right side of the reaction, you're going to cancel out 2 waters on both sides. So you're left with only 1 water on the right side of the equation. And so then the last 2 steps here are essentially just checking to make sure that the balancing worked. So check to make sure it's balanced according to mass, which is to say that the particles, and then check to make sure that it's balanced according to charge. So if you go through that process, you will successfully balance your redox reaction. So let's look at an example here. So we have this unbalanced redox reaction occurring. We have permanganate reacting with oxalate to form manganese 2+ and carbon dioxide. That is indeed a redox reaction. If we assign the oxidation numbers, what we see is that the manganese is going from +7 to +2, so that is a reduction, and the carbon goes from +3 to +4, so that is an oxidation. So when we split these into their individual half reactions, we're going to do the carbon one first. If you remember the rules, the first thing we balance is everything other than oxygen and hydrogen. So we're going to balance the carbons by putting a 2 in front of the CO2. We had 2 carbons on the left, we need 2 on the right, and we get that by putting that 2 in there. At that point, the oxygen is already balanced, so we don't have to add any hydrogens or anything else, or any waters to get that to be balanced. Excuse me. So we have 2 carbons, 4 oxygens on each side. Next thing to do is to balance the charge. If this were in Gen Chem 1, we would have said that we were done there because we got all the carbon and oxygen balanced, but the charge is not balanced. So we have -2 on the left, 0 on the right initially, and so to get the charge to be equal, only adding electrons, we're going to add 2 electrons to the right so that we have -2 on the left and -2 on the right. So that half reaction is now balanced. We could do the same thing with the other half reaction. So if you remember, that was just 1/2 of this overall reaction that we're looking at here. So now we're going, now we're going to look at the permanganate. So the permanganate goes to manganese 2+. So the manganese is already balanced. We don't have to worry about that. But the oxygen is not balanced. So to get the oxygen to balance, we're going to add water. So we add 4 waters to the right to account for the 4 oxygens in the permanganate. Okay? But in doing that, we've now messed up the hydrogen. So hydrogen wasn't even there before, but now it is there and imbalanced. So to get the hydrogen to be balanced, we have 8 hydrogens on the right, because we have 4 waters. Each of them have 2 hydrogens. And so to get those 8 hydrogens on the left, we are going to add 8H+. By the way, the reason we can do this is because anytime we're doing a redox reaction, we are assuming that it is happening in acid solution, unless it is specifically told to us that we're doing it in a base solution, which we'll talk about in the next, maybe the next video, probably 2 videos. Anyway, so there is H+ available for this to actually participate in the reaction. So our hydrogen is now balanced, but our charge is not. If we add up the charges on the left here, we have 8 positives, and then we have a single negative here, which gives us +7 on this side. And then on this side, we just have the +2 from the manganese, and this has no charge. So we need both of these to be the same. The only change we can make is adding electrons. And so to get these two to be the same, whichever side is higher, we just add the number of electrons that are needed to get it to be the same as the lower value, which in this case is 5. We're going to add 5 electrons to the left side so that both of them are at +2 in terms of their charge. So that is the balanced half reaction for the permanganate side of our redox reaction. So now we have both of our half reactions balanced. Now we're going to look at them and see how are we going to get the number of electrons being transferred to be the same for both. Because remember, we're treating these like it's 2 different reactions, but it's not actually 2 different reactions. It is the same reaction that's occurring. And so however many electrons are being given up by this part of the half reaction, we need the same number of electrons being accepted by this half of the reaction. And so to get those 2 numbers of electrons to be the same, we're going to take this half reaction, multiply it by 5, this half reaction, multiply it by 2. Because the smallest number, the smallest whole number, where these 2 things can be the same is 10. If we can only get this in packets of 2, and we can only get this in packets of 5, the smallest number where those will be the same is 10. And so if we do that, we get this. So now we have 10 electrons in both of our half reactions. And when we add these 2 together, which is the next step, we get this mess. This big old mess here. And we can simplify it a little bit by canceling out those electrons, because we have 10 electrons on both sides of the equation. If we have the same thing on both sides of the equation, those cancel out, which then leaves us with this. So we have 16 hydrogens, 2 permanganates, 5 oxalates, goes to 2 manganese 2+, 8 waters, and 10 CO2s. And if you check the equation here, that is the balanced equation for this redox reaction. The carbons are balanced, hydrogens, oxygens, and manganese, and charge are all balanced. Alright, I think I'll call it there for this video. In the next video, we are going to just do some example problems, and maybe if I have time, talk about the basic solution as well. So even before you jump into the next video, go ahead and try and balance these two examples here. Use the rules. Start with rule 1, work your way through the process. As long as you follow the rules, you will end up with the correct answer. By the way, on this one, it looks like it's balanced already, and by Gen Chem 1 measures, it is. But remember, charge is not balanced. You do need to balance the charge, so you do have a little bit of work to do. This is definitely the easier of the two, but there is still stuff that needs to be done here. This is not already balanced. All right, I'll see you in the next video.